저 발표를 영어로 할 건데, 네. The paper I'm going to present today is called Contrast Enhanced Semi-Supervised Text Classification with Few Labels, and it was published in AAAI in 2022. I will follow this order for my presentation. And to begin with, I want to address the challenge that is the reason for this paper, and it is in traditional approaches, often big amounts of annotated data is required, but it is incurring high cost, and also working with limited amount of labeled data leads to overfitting issues. That's why attention on semi-supervised learning has been increasing, because it can be used to utilize unlabeled data. And these semi-supervised learning-based approaches often leverage self-training. And self-training is simply generating pseudo-labels for unlabeled data and using that for further training. However, in this type of traditional approach, they don't perform sample selection or consider noises in the generated pseudo-labels, which might result in error accumulation. It's also known as confirmation bias. And this is considered a severe problem in conventional semi-supervised learning approaches. And in this paper, to overcome the drawbacks that I just mentioned, this framework that is called Contrast Enhanced Semi-Supervised Text Classification is proposed. And later I will explain the steps in this framework in detail. But if we look at the overview, the proposed framework leverages Bayesian neural network to provide certainty estimates for unlabeled data and select the appropriate instances to improve the self-training. And then a reliable similarity graph is built on the selected data instances to enhance contrast and exploit the smoothness assumption. And finally, training on pseudo-labels is reformulated as a new problem, and learning is conducted in a noise-robust manner to elevate the confirmation bias issue. And if we look at the related work, I will specifically mention the baselines that are used in this paper. And the first one is unsupervised data augmentation, UDA. And it performed consistency training by making features consistent between back-translated sentences. And in this type of methods, it requires an additional module to facilitate the main model's training. And if the data distribution between these modules don't match, challenges can occur. And another one that will also be used as baseline in this paper is uncertainty-aware self-training. It utilizes Bayesian neural network to select samples and performs self-training on the selected data. But still, this doesn't solve the confirmation bias issue and doesn't consider the smoothness assumption. And I will now explain the concepts before introducing the methodology. And the first part is the goal of semi-supervised text classification. And it is to learn a mapping function by minimizing the empirical loss. And it can be summarized in an equation like this. And another concept that we should know is self-training. And in self-training, first, the teacher model is trained on the labeled dataset, and then the teacher model pseudo-annotates a selected part of the unlabeled data to form the final augmented data, which will be used to train the student model. Then the teacher model is updated by student model, and this training process is repeated until convergence. And equation 1 becomes equation 2 in the case of self-training. And here the difference is the label part. The label is the hard pseudo labels given by the teacher model W star from the last iteration, and the W here is the model parameters for the student model. And smoothness assumption is basically if 2 points x1 and x2 are close in a high density region, then so should be the corresponding labels y1 and y2. And if they are in low density region, it means that the labels y1 and y2 are different. And the last concept is the Bayesian neural network. In this structure, instead of having fixed weights, it assumes a prior distribution over the model parameters, and the parameter optimization is done by finding a posterior distribution over model parameters W and over the on the training dataset. But this probability is really computationally heavy, and in this paper it is shown that using Monte Carlo dropout, we can approximate this probability by equation 4. And in the methodology section, we will answer some questions. The first one is how to select which unlabeled data we will use for self-training, and how to use contrast among data samples by regularization term R, and how to robustly learn with pseudo-label samples by the classification loss R. And the first step here is the sample selection. We have to select the unlabeled data instances by estimating their certainties. And the certainty measure chosen in this paper is information gain of model parameters. And in equation 5, we can see how information gain is calculated. It is the difference between the final entropy after seeing the whole unlabeled data set and the current entropy in the current iteration, with the posterior distribution of the model parameter also in the current iteration. This equation is also computationally heavy, and we can use MC dropout to approximate it again with this equation. And here, this is a trackable estimation now, and it's not as computationally heavy to compute. And here, a lower information gain value means that the model is more certain about the sample, because this section is close to the final entropy. And this means that model is not going to have wrong pseudo labels, but most likely to have right pseudo labels. But there is a problem, because if this information gain value is low, it means that the model will learn only a little bit from that sample. But if this information gain value is high, it means that the pseudo label is more likely to be wrong. So we, to balance these scenarios, we sample data instances with different sampling weight, and this is how it's calculated. Instances with lower information gain will be sampled more, and if it's higher, it will be sampled less. And here the denominator is just normalization factor. And second step is constructing the similarity graph. Similarity graph based on pseudo labels is built, and the unreliable edges, which we will define what this is later, are pruned to create a reliable similarity subgraph. And then the model is optimized under the guidance of this graph. Here, the initial graph has the node set V and edge set E, and it is an undirected and weighted similarity graph. The weight is assigned based on if the two nodes have the same hard pseudo label, the edge weight between them is 1, and if they have different pseudo labels, it is assigned as 0. And after the similarity graph is constructed, this can be used to enhance the contrast during training. We enhance the contrast with this regularization term R. Here R is vital for data efficiency because it takes the underlying information from data instead of just using the data to separate the classes. And it also explicitly forced the model to follow a smoothness assumption. And for the reliable subgraph construction, from the initial graph, we need to prune some of the edges because there are some wrong weights due to wrong pseudo labels. That's why we add an attribute reliability to each node and each edge. And for node reliability, this is how they calculate it. And since this variance section takes value from 0 to 1/4, this is always going to be positive. And again, here we use the MC dropout to do the approximation. And for edge reliability, we use the two node reliability values and take their average. And if this value is high, it means that the nodes with this edge are more likely to have correct pseudo labels. And the top K edges with the highest edge reliability values are taken. And we create the subgraph. And the regularization term I explained in the previous slide here is edited with the new graph. And this time, since we have less edges, it was n edges before, and now it's k, and k is much smaller than n in this case. We not only improve the performance, but we also reduce the time complexity. And the third step of the methodology is the robust learning. Utilizing traditional cross-entropy loss is prone to error accumulation in this case because it weighs more on difficult samples during optimization for faster convergence. And difficult samples mean that the model is finding it challenging to make prediction. And when labels are noisy, when we have more wrong pseudo labels, incorrect labels make the difficult data. This makes the model memorize the wrong information aggressively during optimization, resulting in confirmation bias. This is why they utilize this partially hybridized loss. This is the recent most advanced noise robust loss, and they integrate the cross entropy loss too. And finally, we have this loss function that is used for this classification task, and this apparently ensures the robustness. And for experiments, they use 5 data sets. IMDb, ELEC, and SST2 are used for sentiment analysis, and DBpedia and AG News is used for topic classification task. And for the experiments, they take 30 labeled data per class for training and validation and use the test set in the original data set. And the rest data are added to the unlabeled set. Here, they use 4 baselines. The first one is the bird, directly fine-tuned on the small label training set without using any unlabeled data. Second is UDA, which I explained before. And third is standard self-training. This is without considering any sample selection, feature relationships, and confirmation bias. And the last one is USD, which is the most similar one to the proposed framework here. But it still doesn't fix some of the problems. This is the settings for the experiment, and this is the overall results. And with only 30 labels per class, the model consistently achieves the best performance. And this one, the BERT, without using any unlabeled data, performs the worst because the labeled data amount is really insufficient. UDA outperforms that, but it uses an additional module, which is which in this framework, it's better. Standard self-training performs good too, but the UST and UDA are the best performance models. And also here, the proposed framework is only 3% shorter than fully supervised learning, which shows that it is also performing well. And to see the effectiveness of the reliable similarity graph, they have done TSNE visualization on the news data set. And from A to C, it can be clearly seen that the clusters are more clear, which shows that it can be used to enhance the contrast. And here to see the effectiveness of the noise robust loss, the solid lines show if we use noise robust loss, and the dotted line is without it. And initially we can see that they perform similar, but with time, when we use this loss, it outperforms the dotted lines in most cases, since the error accumulates with iterations. It shows that it's important to use this type of loss. And for ablation study, the performance is the worst when sample selection is removed, since noisy labels will corrupt the training. But overall, the other parts of the framework affect the final performance almost the same amount. And lastly, to see the limit of the framework, they took only 10 labels per class, and it still outperformed USD except in one data set. And it can be seen that it can work with even less labeled data. And here in figure 4, to see how the number of labeled data affects the performance, they use different numbers of labeled data. And as expected, the performance improves when the number increases, but still there is a small difference between the instances, showing that this framework is data efficient. And yeah, to conclude, this framework wisely selects the unlabeled data for self-training, and it uses a reliable similarity graph to consider smoothness, and it mitigates confirmation bias by proposing a new formulation and by using the noise robust loss, and it outperforms the state-of-the-art semi-supervised learning approaches through experiment on 5 benchmark data sets. And that's it.
Okay, thank you for your presentation.
Yeah.
I wonder that what's this method is semi-supervised learning. I feel that all the process are performed by fully self-training.
But it's only using 30 instances for the label training data.
Then could you explain in the framework overview video in the page 4?
Oh, this one, yes.
Then here, which step we have the 30 pre-labeled data before step 1?
Because these data sets they use, it's labeled already, and they are taking only 30 instances from that, but act like the rest is unlabeled. This is what I understood, but yeah, they take as if it's unlabeled and compare the result at the end based on that.
In the experiments, standard ST, standard self-training, we compare to the method, which parts are different from the standard self-training?
The sample selection is not performed in traditional self-training. here with different sampling weights, they are taking the more significant samples, I think. And also the graph improves the contrast, and the loss function is also different. So this is why it outperforms the standard one, I think.
Does standard self-training only depends on pseudo labeling?
Yes. This is how it's sorry. This is how it's what is defined in the paper. So yes.
다른 질문 있어요? 베이지 학생 한국말도 잘하기 때문에
네, 한국어로 해도 됩니다.
질문. Actually, I cannot fully understand about how to construct graph for regularization. Could you explain it again?
From what I understand, here the features are in the feature space. They take the after they do the graph, the features are separated based on classes, and this shows which features are similar in one class and which features are different between classes. But for constructing, they are the edges are sorry, the nodes are just the text sequence based on the paper. So they just take the text sequence, and if they have the same pseudo label, the edge weight is 1, and based on this weight, I think it's clustering. They perform clustering.
Each node is defined by a sequence of text.
Yes, the nodes are the sequence of text. Which here in the experiments, I think the token length here states that sequence of text also.
네, 또 다른 질문 있습니까?
질문 있는데 그
네.
인트로덕션에 나오는 거 보면은 지금 보면 similarity reliable similarity graph is built on a selected data instances to enhance the contrast and exploit the smoothness assumption이라고 나와 있는데 그 각각의 노드가 데이터 인스턴스가 아니라 지금 그럼 각각의 그 클래스로 정의가 되는 건가요? 클래스의 집합으로 정의가 되는 건가요?
그거 어디에서 나와요, 혹시?
그 introduction CEST overview 거기에
네.
두 번째 볼렛에
잠시만요. I will explain in English, but if they,
Okay.
from what I understand here, the smoothness assumption just shows if the data instances are similar, if they have similar same pseudo label, they should have the same features, and we can see that on the graph. And if they have different pseudo labels, they should have a contrast in the features. So I think to see this is why they construct the graph. Is this the right question? Sorry.
So 그 노드가 그러면은 각각의 클래스로 정의가 되는 건가요? 각각의 클래스에 해당하는 그 데이터 인스턴스들의 집합으로 각 하나의
네.
클러스터가
네.
각각의
여기
노드 되는 건지.
이 데이터셋으로 만드는데 여기 class is 4 and here also the clusters is 4. So yes, I think based on the classes, the clustering is done.
Then what is the purpose of the graph? 그 similarity graph.
To see which features are responsible for which class, I think, because if they consider reliability, the clustering is done better. This is, I think, to check if the pseudo labels are assigned right based on the features. I don't know if how I should explain better, but yeah.
네, 알겠습니다.
네, 또 질문 있어요?
저 질문 있는데 그
네.
익스페리먼트의 어빌레이션 스터디에서 without sampling에서 샘플링은 그 수도 어노테이트의 샘플 셀렉션을 말하는 게 맞나요?
The part here, the sampling part they mention is this part here, the certainty estimation, sorry, wait. Here all of this calculation is proposed in this paper. So without doing any of this, not using any certainty measure, yes, I think that's what it means. And because that's one of the main point of the paper, I think that's why it affects a lot.
감사합니다.
네.
So I have a question. So
Yeah.
as you mentioned, as the information gain is higher, the sampling probability is getting higher. So it means you have to filter out the more certain features or samples in the framework, right?
If information gain is high, it's sampled less actually because
Samples. Yes.
yes, here based on the sampling weight, this value, if this is high, it's sampled less.
Okay. So the sampling is based on the MCMC sampling.
The sampling is based on this value only, from what I understand. Yeah.
So
Only for the
MC dropout-
calculation.
MC dropout is used when is the MC dropout is used after they sampled out based on the information gain. Then after that the MC dropout is used for.
MC dropout is not used in the sample selection method. It's used in this calculation. Because this calculation is hard to calculate. To get the second equation here, they use the MC dropout.
I just confused with MCMC sampling.
No, yeah. The sampling is only based on the information gain value, not MC dropout.
Okay, thank you.
You're welcome.
또 질문 있습니까? 네, 의견 듣고 있습니다.
네.
네,